I'll move on from this slide unless anyone else would like specifically anything else they wanted to know on this subject. We can come back to it later if it seems important. Perhaps the first point I wanted to make was, it's gone now, but I was talking about at this point, you have this energy defined by this bond breaking. And this energy difference is defined by the fact that you've broken one bond, H2 is broken, just an H now, but you've made a new bond. So it's really the energy of these bonds which is deciding whether this is exothermic or endothermic, whether it's more or less energy at the beginning or the end. So we can actually sort of study that in a way by looking at bonds. I mean, if you have a molecule, it's really just made up of individual bonds. For example, CH is a C connected to an H. CH4 is C connected to 4 H's. So approximately, the energy of a CH4 is about 4 times the energy of a CH. Because the energy we're talking about is in these bonds. That's the critical thing. And so what we have here is a list of energies for different kinds of bonds. So this is not the NH molecule. This is an NH bond. So if you had ammonia, NH3, which is in nitrogen in the middle, and 3 H's around it, then really there's 3 of these bonds in the same molecule. So the total energy would be 3 times this. And there's a bunch of them there. So what that means is if we have a reaction like this one, which is just like the previous curve, where you're breaking one molecule apart and it's forming a new molecule, we can work out the reaction energy just by calculating the energy of the bonds you've formed minus the bonds you've broken. So in this example, this N2 bond has been broken. That is an energy of, okay. I should make one more point then. Okay, so the N2 molecule, if you were to draw a kind of diagram of it, is an N with an N, and HCN molecule, that's okay, is an H, like that kind of. What is a triple bond? Another one. Here's one. Okay, there we go. Okay, no worries. So an N2 molecule has a triple bond because we won't go into this detail, but there's 3 electrons in an N that can bond, so they join together like this. If you have an H2N2 molecule, 2 N's with an H's on the end, then it's a double bond in the middle. So that has a different energy. Double and triple N2 bonds have different energy. So that means if you have to kind of not just what molecules are written next to each other, but how many electrons are bonding between them. That's a detail which I think we won't need to go into. But anyway, in this reaction I've shown here, then there's a CH molecule, N2 molecule, breaking one bond and forming a new one. And the bond that's broken is N2, so that's the triple N2 bond. The bond that's formed is, ignoring the H, because if you have the valence electrons of the N atom is 3 electrons which are not in a shell, basically. So they're kind of free to bond with their environment. They're not already, it's a fact. And in this case, the H is still there. I've turned it around, but it's the C in the end that's the new bond in this molecule. So that's the C in the N bond has 293 kilojoules per mole of energy. And so I don't know if you remember this unit. This is the crazy unit chemists use, so we'll stay with that. 293, and so we're breaking 293. So we're forming a 293 kilojoule per mole bond. That's this one. And we're breaking an N2 bond. So overall, when we're not gaining energy from this reaction, we have to put some in because we're breaking a strong N2 bond and making a relatively weak CN bond. And the amount of energy is, if you take the difference, is 648 kilojoules per mole, which, if you remember, we can always think of an energy as being like a temperature. It's like wave numbers in energy. It's not the same thing. But if we always multiply by Boltzmann's constant K, then it's proportional. And it's convenient because it tells us if we have a reaction energy of this much, it means that it needs a really big temperature to overcome that energy. Yeah?
The same question. Why do we choose the single bond of CNN instead of the double or triple? On the last column.
That's a good point. That's actually a mistake. On my part. No. Sorry. Well, your question was okay. So yeah, the slight problem with the example. So one way to draw a carbon atom is a carbon with 4 dots around it, meaning it has 4 electrons that are not paired with other electrons. The nitrogen atom, on the other hand, we have 3 dots around it. Oxygen, we have 2. And hydrogen just has 1. That's one way to think about it. And so the N2 molecule from that looks like this because of the 3 dots. There's 3. This represents three dots from both sides. There's 6 electrons between the 2 N2s, which are free, and they form a triple bond. That's a fact. Carbon, on the other hand, let's do it this way. Has 4 electrons, where hydrogen has 1. So each of these lines represents one of the carbon electrons and the one hydrogen electron. The problem is, which you've just kind of pointed out, is if we have this molecule, HCN, then there's 1 electron here. That forms 1 bond with the carbon. But these 3 should bond with the other 3 carbon electrons. What that means is that this number, 293, should be 891. Fortunately, it's still negative, so my point is still good, somewhat. But this is not 78,000 Kelvin. I guess it's more like 7,000 or even less. It's more like 3,000 or 4,000 Kelvin, I think. Yeah. About 3,000 Kelvin. Okay, that's still a very high temperature. So what that means is that you need a temperature of about 2,000 Kelvin for 2 particles to come together fast enough to break the N2 bond and form the HCN bond. Meaning, they come together, they break the N2 bond, and then they form the HCN bond. And to break the N2 bond, break this bond, you need this much energy. And to form this bond, you get some back, but then it's still more than previously. So if that's the energy we have on the left, she's back. Okay. So it's the same as that picture. We have this reaction energy due to breaking the N2 bond, and then you get some of it back forming the HCN bond, but now the final energy is more than the beginning. That's a endothermic reaction. Okay, the final point I wanted to make was that if you have more than one bond, like H2O, and oxygen has two H's attached to it, then the first one you remove and the second one you remove don't necessarily have the same bond energy. This is only approximation. So, for example, the first H2O bond, making an OH plus an H, just snap off one hydrogen, requires this much energy, 493 kilojoules per mole. But the second bond between the O and the H is a bit less. So it's not exactly precise calculation, but it's a approximation. Okay, so which is the most confusing part of that part? Or maybe.
Knowing the number of bonds you have to break.
Yeah.
Will be tricky.
Yeah. Okay. Well, I'll try and always include these lines to make it clear which bond has been broken. But the reason it's okay. So this picture has pretty small molecules, 2 atoms and up to 3 atoms. And we have this coordinate where they come together and separate. And this we won't study at all, but if you have a very complex molecule like benzene, this is this ring. It's not quite benzene because a benzene has 6 carbons, the black dots, with 6 hydrogens. One's missing in this case, but it's almost like benzene. And it's reacting with another molecule with 4 carbons and 6 hydrogens. And so this is the reaction pathway. So unlike before, when you get to the end of the reaction, you have a new molecule. It turns out the energy has gone down. So this is an exothermic reaction. So it's release some energy. But on the way, it has lots of different configurations, not just breaking one bond and joining another, but breaking a bond, twisting the molecule, forming another bond, breaking that one, forming a new one. So the reaction pathway is a lot more complex, and you have lots of different transition energies, lots of different reaction barriers to cross on the way. So this we won't do at all, but this is interesting because this is kind of the cutting edge research in the chemical physics of reactions, because to calculate these energies in this path and the shapes of these molecules that you form on the way is really interesting, but of course quite difficult. So that's, if you get into the subject, this is what you'll do. Okay, so this one, the reason we're interested in the energies is to do with equilibrium. We already had an equilibrium to do with the fact that the collisions between molecules and the rotational excitation of molecules, if there's enough collisions, the density is high, they'll form a common temperature. That's an equilibrium. Same thing happens here, because if you have a reaction, AB plus C goes to A plus BC, so the B is moving, we're breaking AB bond, forming BC bond, and I've drawn it as a double arrow because they could collide again, and the exact reverse thing could happen. There's no kind of fundamental reason why that couldn't happen as well. And exactly like if you have a collision between, two molecules, it could make the rotational level increase or decrease. Both things can happen. And so that double arrow means really there's no reason to think one direction is more important than the other, except that this might be a familiar formula to you now. The densities of these two options, AB or BC, in a 1 centimeter cube box is going to depend on the difference in their energies, and we just calculated the difference in their energies, and it's going to depend on the temperature. Except the temperature now is the chemical temperature, so this is an entirely new temperature. And it might seem frustrating that we keep introducing temperature, which is the relatively abstract concept, but it's the one thing that makes chemical reactions and rotations and blackbody radiation fields and kinetic velocities, it makes them all the same thing, because you can relate one to the other through a Boltzmann equation and say that if there's enough collisions, the temperatures will be the same. And it's a really powerful statement, which you assume a lot, but actually isn't, that isn't necessarily going to be obvious until it turns out to be true. So Okay, so what that means, delta E, if it's endothermic, means this is a negative number. Yep, okay, so if this is a negative number, that's negative, so this entire term will be positive. So you get an exponential number to the power of something positive. And if it turns out that's greater than 1, then you're going to have a large amount of AB versus BC. If this is a positive number, then this becomes a negative term, and the reversing happens. You have a lot of BC rather than AB. So if it's endothermic, then you have a negative delta E, and this means you're going to have a larger fraction on the top than the bottom. Let me do the example. Yes, okay. H2O, OH plus H. So here we're breaking a bond, H2O. We'll do it explicitly this time. Okay, so H2O has 2 single bonds to the hydrogens, which on our table is single bond between the hydrogens. Okay. Whereas on this side, we've only got 1 bond, so it's even the same bond. It makes it a relatively simple thing to calculate. Oh, 493. Okay. And at some point, I updated my table from 493 to 459. Okay, so 460 approximately kilojoules per mole on this side, 2 times 460 kilojoules per mole on this side. So if you put that in the formula, that is this 493 because to do with this average bond thing I talked about earlier, there's a slight difference between 459 and the real value, but it's close. Times 10 to the 3 because we want to convert from kilojoules per mole to something more rational. So I converted that to joules. So times 10 to the 3 will convert kilojoules to joules. And this is per mole. So this is the amount of energy if you had an entire Avogadro's number versus of bonds. So if we divide by Avogadro's number, which is huge, we get the amount of energy in the bond in joules for 1 molecule, which is tiny. That's fine, because then we divide by Boltzmann's constant, which is also tiny, and the temperature. Okay, you get a number 0.994. Oh yeah, that should be negative, yeah.
So that should be positive, right?
Yeah.
Does it keep giving the same result?
Okay, so what have I done wrong?
It will be a little greater than 1, right?
No, it's positive. Sorry, I take it back, it's positive. This is correct. The reason is the delta E is the no. Okay. Yeah, no, okay, so So, yeah, no, you're right. So these two should be the other way around. That's actually the way to think about it. What do you think about that? Okay. Okay, yep, I see the problem. So for the rotational problem, the formula was right. Okay. Anyway, the final result somehow is this minus sign is wrong, I think. The idea is if you have a okay, yeah, right. So okay, yes, okay. So what we're saying here is that this is for rotation. Sorry, that's a good metaphor to go on to. E1 is greater than E0. That means the molecule is rotating faster, right? It has more energy. In this case, H2O has more energy in the bond. One of the bonds is broken. So I've written this as 400 kilojoules per mole. This one is 2 times 400 kilojoules per mole. But this is the one with more energy. The reason is that the energy, like if we're standing here on the Earth, we have gravitational potential energy. If we stand on the International Space Station, we have more gravitational potential energy. So by actually separating we're separating us while we're attracted to the Earth, we're increasing our energy. So by breaking this bond, you're not decreasing the energy of the molecule, you're increasing its energy. Because ultimately the OH and the H feel a force towards each other because of electrostatic attraction. So what that means is that here we have minus the higher energy state minus the lower energy state, which is this is the higher energy state and this is the lower energy state. But if you were to write that as that way, you should make this a minus energy, because by separating the bonds, you're making the energy lower. So we can either make that a minus energy or make that a plus. So that's the mistake. This should be a plus here. Because even though I've written this as a smaller number, by breaking the bonds, you're increasing the energy of the system. Does that make any sense? Somewhat.
Yeah, but in that case, that number would be like 0. Like that.
Okay, so we delete that minus sign, but keep everything else the same. So now the delta E is, I won't go back to it. I'll write it here in fact. So delta E is the energy of OH plus H minus the energy of H2O equals 2 times 493 minus 493. No, other way around. So that gives us the negative number here. So sorry, that's an unnecessary confusion. I'm sorry to introduce that, but okay. So, yeah.
What we just noticed is that we actually did the calculation in the calculator.
Yeah, what do you get?
That exponential actually gives 0, right? Like, that's a really big number, so the exponential minus that number is practically 0. Not
Okay.
0.9.
Maybe it makes sense, no? Because it's not too, I mean, the direction can go both sides, but the probability
Yep.
should be different.
Yep. I mean, the answer is definitely about right, and the reason for that is, I mean, if you form this H2O molecule, we know that it has. I mean, to break off one of the hydrogens requires energy. It is a bound, stable molecule, so that at a very low temperature they collide so slowly, it's very unlikely that it'll break off spontaneously. So this is definitely the right answer. Is this the right value of Boltzmann's constant? Okay, I'll tell you what, we'll come back to this one. But the main point, if you ignore everything except that point and this point, is that if you have a low temperature, 10 Kelvin, then once a bond forms, there's not enough collisions between particles, or if the collisions are so slow because the temperature is very low, it won't break again. So you'll have a lot more H2O than you will have OH because there's more bonds in H2O. That's a bit confusing, but I guess we'll come back to this next time. Because the final conclusion of that, coming back to interstellar space, where the temperature is 10 Kelvin, and where these are the only elements that you really have of any significant number, and most of them are hydrogen, and helium isn't chemically important because it's a noble gas, it doesn't react with very much. Then if you combine all the molecules together to make the most number of bonds. So our idea is at low temperatures, if you form a bond, you won't be able to break it again. And you combine them all together, this is what you get. And the reason you get these kind of molecules is let's think about ammonia, because we've not talked about it before, NH3. So there's a nitrogen with its 3 valence electrons, and for every nitrogen there's 10,000 hydrogens. That's the elemental ratio approximately. So it's surrounded by hydrogens continuously, which are moving with velocities depending on the temperature, so they're all moving about. And the idea is that sooner or later it'll collide with a hydrogen and form a bond. I mean, it could also, occasionally there's also a carbon somewhere as well, moving about. But there's 10,000 times more hydrogens than carbon. So the probability of that nitrogen colliding with a carbon is very low. So that given this nitrogen surrounded by mostly hydrogens, over time it'll form bond with hydrogens because that's what it's likely to collide with. And then you end up with NH3, and that's the maximum number of hydrogens it can bond with. Nitrogens can form 3 bonds. And so that should be the most final stable molecule you'll form with nitrogen in it. I mean, it could occasionally bond with a carbon, but those collisions are so rare, there'll only be a few molecules with nitrogen and carbon in the same molecule. That's kind of non-mathematical, but actually pretty convincing argument about why these are the molecules you should find in space. If you think about equilibrium. So this is if you have enough collisions that all the equilibriums become equal. But the problem is if you actually look at the observations of what's observed in space, specifically in an interstellar cloud. Remember we had translucent or interstellar clouds you could see through, and we had the dense ones which you couldn't see through. And they're important because that's where you have this low temperature. And also we have the high densities, and we have lots of collisions. And the ones in the translucent interstellar clouds, the diffuse ones that you can see through, there's far fewer collisions because there's far fewer molecules in a cubic centimeter. Anyway, so if you look at enough clouds, this is what you measure on average. We measure 1 for H2 because that's our standard for density of 1. We're measuring not the density of things, but we're measuring the relative abundance of things, the relative density. So that's going to be the density divided by the hydrogen density. And the hydrogen density is the density if we add up all the hydrogen nuclei, all the elemental hydrogen in the cloud. And in this case, I've said H2 is equal to 1 because in a dense cloud, there's very little atomic nitrogen and mostly molecular nitrogen. That's a detail, it doesn't matter. So this is our standard, 1, and everything else is compared to hydrogen. And they're all about 1 in 10,000 or less. And only when you get to this level, 2 times 10 to the minus 8, it means 1 in about 100 million. Then you finally get NH3, which is one of the ones we expect from having this thermal equilibrium. And water is all the way down to 10 to the minus 9, so that's 1 in 500 million. 1 in 200 million, sorry. Even though that should be one of the most common molecules in space. And I think methane is not even on this list. You can't even see methane in this context. So the point is that all the equilibrium stuff means you have a lot of collisions to make all the kinetic, rotational, and all the other kinds of temperatures the same. And it's not happening here. This is not an equilibrium. And that's because even though a cloud lives for a long time, a dense cloud survives for about 10 million years at least, possibly longer actually, but 10 million years is a pretty reasonable guess. And if we do the calculation, which we actually looked at earlier, then the time to reach the equilibrium, given enough collisions, is about 10 to the 7 years. Let's go back quickly to this picture, where we had the time between two-body collisions is about 14 days. And if you calculate how many two-body collisions you need to produce all the molecules into their most equilibrium state, so what we're looking at is the changing abundance. And the equilibrium is when we get to the end here where it's no longer changing with time. It's the definition of abundance. And so some species reach equilibrium in about 1,000 years, whereas others require 1,000,000 years. And if you tweak parameters, you get the 10 to 7 years. So it's variable, but it happens. And I guess the other point worth making as well is that, which I haven't described, is that the equilibrium is based on the collisions between particles. So that depends on the kinetic temperature. But there's also other energy coming in as well. I mean, we previously had the cosmic microwave background as a second kind of energy source. That won't affect this. It's too weak to affect this. But there's another source of energy, which is cosmic rays, where throughout the entire universe you have high energy particles streaming through stuff, even through us. You probably might have studied this. And so the cosmic rays are also providing a certain amount of energy which disrupts the equilibrium, the same way that the C and B disrupted the equilibrium down here. But yeah. But the main point is that it's not, things aren't existed long enough to reach the equilibrium. Yeah. Okay. Okay, and maybe there's only 5 minutes to go, so we won't start the next bit. But I think tomorrow Carmen said she'd probably visit this room. There's no official classes tomorrow, or no required classes, but I think she said she'd be around to work on things in the afternoon. And the idea was to finish this, begin the next exercise already, which we could have worked on, but we haven't finished it yet. That's my amazing planning. And so I'm not sure that I'll be seeing anyone myself tomorrow, but I did some time ago make another thing. Must be that. If this is I'll turn it off because it's an image. If this is an ALMA image, and you might have created ALMA images today, possibly, where this is the size of the ALMA beam spot. So that's, you know what that is now. And this is a source where you're observing the lines like this, the isobars, the contours. That's black body thermal emission. So that's looking at something hot and dense here. And the blue stuff is carbon monoxide emission lines. So this is individual rotational emission lines. And this is quite small. This is about 100, this is about 700 AU apparently across the entire disk, maybe that direction. And the idea is that you're looking at a protoplanetary disk with a star in the middle surrounded by the material that will be a future planet, basically, and fall on the star as well, some of it. And if you look at the CO, but if you look at the spectrum of the CO, then this is what you see. You see, this is frequency, just like you measured before, and you see an upward going curve, which is the black body emission from the dust. And then you see some lines, which are the rotational lines of CO. So you were studying the J equals 1 to 0 rotation, which is at 115 gigahertz, you remember, which is way off the scale somewhere. So this is other CO rotational lines for higher J's. And in the spectrum, then you can make a graph, which we didn't really talk about in any detail, but is important in astrochemistry, where each point tells you this is basically the ratio N2 over N1, basically, on this side. And each point tells you the ratio N2 over N1 for one of those transitions that you're seeing. And by looking at them all together, then you can work out the temperature. This is a different equation than we used previously. So anyway, so the other project which I wrote first but decided to do the previous one exists. And the idea is for that one is that you can use a real spectrum measured by ALMA and of a real protoplanetary disk, and you can measure its temperature. So that would be your optional exercise. If you didn't want to go be in the sun tomorrow or whatever you do normally, you could come here and do that. That's my offer. But I'll be here at 12 with Carmen, I guess. I'll put it on the course website as an optional something. Yeah. Yeah. Or you can do it at home and talk about it. It's fine. But this one's cooler than the other one actually because it's got real data in it. But it's one step further, I think. So. Anyway, it's 5 o'clock, I think. So let's not keep going to the next thing. And otherwise, I'll see you tomorrow. Small chance, or I'll see you on Thursday, and we'll lecture some more about chemistry. And I'll find out what the ratio of H2 over OH is.